Welcome to derivatives. The derivative of a function is the limit as h goes to 0 of the difference quotient. Now, geometrically, what that is the slope of the tangent line. So if this is the point x naught, f of x naught, then f prime of x naught is the slope of the tangent line at that point. And so there are many different notations for derivatives. And I've just listed a few here, and I've listed the ones that we're going to use the most often. Leibniz notation, like dy dx or df dx, and then Lagrange notation, which is the prime notation. All right, so let's do an example. Let's find the derivative of f of x equals 1 over x, and then we'll find an equation for the tangent line. So I'm going to go through this computation for part A fairly quickly, since we did this computation actually last week. So f prime of x, I'm using the definition right here, is the limit as h goes to 0 of f of x plus h. That's 1 over x plus h minus f of x, which is 1 over x, over h. Now that's a complex fraction, so I'm going to multiply the top and the bottom by x plus h times x over the same thing to clear out all my denominators. So that's the limit as h goes to 0. On top, I need to distribute this to both fractions. I get x minus parenthesis x plus h. And on the bottom, I just get h times x plus h. Now, if I distribute on the top, I'm going to get a negative h. Finally, I can cancel those h's so that I'm not getting 0 over 0 when I take the limit, and you do have to write the limit sign this whole time. Now I can take the limit, set h equal to 0, and I get negative 1 over x squared. So f prime of x is negative 1 over x squared. That's the derivative of that function at any point. So geometrically, this is the graph of y equals 1 over x. F prime, the derivative, is the slope of the tangent at any x. So we can see that that slope is always negative because you're squaring x and then there's a minus sign. So sure enough, no matter whether x is positive or negative, the slopes of my tangent lines are negative. Okay, so now let's find an equation for the tangent line at x equal 2. So that might be about here. So we need two things for an equation of the tangent line. We need the slope. So m is going to be the derivative f prime evaluated at 2. So f prime of 2 is negative 1 over 2 squared, which is negative 1/4. So that's my slope. And I need the point on the line. So I'm given x is 2. So this is my x naught, y naught in point slope formula. My x is 2. To get the y naught, I want f of 2, not the derivative, not f prime, but I want the value of the function at 2. That's 1/2. All right, now I use point slope. Y minus 1/2 is m, which is negative 1/4, times x minus 2. And then if I want to solve for y, I can get y equals negative 1/4 x, and then that would be plus 1. And there's my tangent line. Okay, you should pause the video and practice and do this one. Okay, hopefully you did that. Let's do part A, f prime of x. So let's watch your notation here. This is the limit as h goes to 0. The whole time we're going to need an h in the denominator till we take the limit. On top, I have f of x plus h. That's 1 minus 4 x plus h minus x plus h quantity squared. Then you want a minus and a big set of parentheses, and then f of x goes in the parentheses. Okay, now we need to do FOIL on the top and distribute. So that's the limit as h goes to 0. Keep that h in the denominator. In the numerator, I get 1 minus 4x minus 4h. Now I'm going to do FOIL minus x squared minus 2xh minus h squared. And now I'm going to distribute this minus. Minus 1 plus 4x plus x squared. Okay, a whole bunch of things cancel. X squareds, the 4x's, and the 1's. Now, there's 3 terms left on top. Each one has an h in it. So I'm going to keep my limit sign here and factor the h out. H times negative 4 minus 2x minus h over h. Finally, I can cancel those h's because I'm canceling from a product, not a sum or difference. Okay, and now that's the limit as h goes to 0 of -4 minus 2x minus h. And I can set h equal to 0, find the limit by substitution, and I get -4 minus 2x. And these are all equal signs. These are not arrows. The result is f prime of x is -4 minus 2x. Okay, part B, for what x is the tangent line horizontal? The graph of f is a parabola. It opens down, and so the horizontal tangent is going to happen at the vertex. So what we want to do is set the derivative equal to 0, because horizontal tangents have slope 0. So we set -4 minus 2x equal to 0, and we get x equal -2. And if you remember from pre-calculus, the vertex formula for a parabola, -b over 2a, we could have found that value by just finding the x coordinate of the vertex. But this is a fun way to do it. Okay, so 3 items of interest. Derivatives of linear functions. The tangent line to a graph is the best linear approximation of that graph at a point. Well, if the graph is already a line, then the tangent line is just the line itself. So if you have a line like y equals -3x plus 2, the tangent line is the same line. And so the slope of the tangent line, y prime, would be -3. And that's constant. Everywhere the slope will be -3. And we'll use that on the next page. Okay, if s is position, then the derivative of s with respect to t is called velocity. And if we take the derivative of velocity, we get the acceleration. Now, the derivative of velocity can also be thought of as the second derivative of position. And second derivative is denoted with 2 primes. And then third derivative would be 3 primes. More on that later. Okay, since the derivative is the slope of the tangent line, that number will not exist in certain places. It will not exist wherever there is no tangent line. So there will be no well-defined tangent line at corners, at cusps, and at discontinuities. There is a tangent line where the tangent line is vertical, obviously, because I mentioned tangent line, but the slope of a vertical line is undefined. So the derivative of a function is not defined anywhere there's a vertical tangent. So those are the big places where derivatives don't exist. And now we're going to graph some derivatives. So for this first picture, I'm going to use the fact that for a straight line, the derivative is just the slope of that line. So between this point and this point, the slope of this line, m, is I go 1 over 2 down, so -2. Between this point and this point, the slope is 0. And then between these 2 points, the slope is 1. So to graph that, I'm going to start over here at -2, and I'm going to go 1 unit over, and I'm going to put a hollow dot because the derivative doesn't exist at corners. So then I jump up to derivative 0, and that goes all the way to x equal 1. Another round dot, and then I jump up to derivative 1. Hollow dot, go over, and then endpoint. So when you have a bunch of straight lines, you can graph the derivative very precisely. In the next 2 pictures, you just have to kind of wing it. The things you're looking for are horizontal tangents, because that corresponds to 0 derivative. So the graph of the derivative will pass through the x-axis when x is 1. Then you're looking for just whether the slope is positive or negative. So the slope of this curve is positive when x is less than 1, and it's negative when x is greater than 1. So I'm going to have positive numbers getting closer and closer to 0. There's my horizontal tangent, and then negative numbers. Now, I don't know that the derivative is a straight line. It might be slightly wavy, but that's good enough. Okay, next one, there's 2 anchor points. Horizontal tangent at x equal -1 and +1. So I'm going to cross the x-axis here and here, and then positive slopes, negative slopes, positive slopes. So I'm going to go positive, pass through 0, negative, 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 and then positive again. And that's a rough picture of the derivative. So over here, if I didn't mention it, these are my functions, y equals f of x, and these are my derivatives. Okay, we're going to end up with a big theorem on differentiability and continuity. If a function is differentiable, then it's continuous. So differentiability is stronger than continuity. It doesn't go the other way, as this example illustrates. So we're going to use the graph over here to answer these questions. Where's f differentiable? Okay, all x except, I want to look for the bad spots. Corners are bad, so that's at -1. Discontinuities are bad. I have a discontinuity at 0 and then at 2, because there's a hole at 2. Where's f continuous but not differentiable? So of those three numbers, -1, 0, 2, where's the function continuous but not differentiable? Well, only one of them, x equal -1. The function's not continuous at the jump discontinuity and at the hole. Okay, where's f neither continuous nor differentiable? Okay, that would be the other 2 points, 0 and 2. And the last question, where's f differentiable but not continuous? Well, that's a trick question. This can't happen by the theorem above. Okay, so in the next section, we're going to learn shortcut rules for taking derivatives, but it's important to also be able to take the derivative using the definition like we've done in this lecture. And that is the end of this section.